My name is Jeff Sukharev, and I come to you from Ancestry.com, the world's largest genealogy service company. In this talk, I'm going to talk about the problem of finding alternative name spellings. It's an important problem in name matching, part of record linkage. So we started working on this project while working on several problems for Ancestry.com, including search engine optimization and also including three-node deduplication. So first, a few words about Ancestry and Ancestry products. Over the years, Ancestry accumulated over 60 million user-generated family trees and over 16 billion personal records. So here on the left side, you see a typical example of a family tree where nodes represent individual people and ages represent relations. On the right side, you see kind of a basic example of a scanned documents. And we have multiple types of documents. There could be birth certificates, death documents, death certificates, military records, census data, also newspapers, journal, and lots of other historical documents. One popular way of interacting with Ancestry data is using Ancestry search. Ancestry search is basically a form-based search where users specify names, locations, dates, anything they know about the person they're searching for, what could be actually found on the form. And then the result of this search, the output is basically a collection of relevant records found for the information that user provided. Unfortunately, very often user doesn't exactly know what's the right spelling of the person they're searching for, due to multiple reasons. Maybe they just don't know the right spelling, or maybe the spelling has changed, or maybe the documents contain errors, or there are also OCR errors as well. So the idea is that it's either user has to be really aware of all possible variations of the spelling, and some users do, like professional genealogists. But most users do not know this information. So the idea is to do it automatically. So we would actually help user to find the credible list of alternative name spellings. And that way we'll actually improve search and improve the recall of relevant documents. So what are the typical example of kind of alternative spellings of the different last names, for instance? And we're looking here at the Western last names. So if you see a few examples, for instance, McDonald can be spelled with an M-A-C. It can also be spelled as an M-C. Clark can be spelled as a Clark without E at the end, can be spelled with E at the end. You see other examples here. So clearly it seemed to us when we started this project that there must be a good way of finding kind of the list of alternative name spellings. There are existing methods out there, but most of those methods are rule-based. For instance, there are phonetic methods that return basically a list of similar sounding last names. There are also kind of edit distance or similarity metrics. So we wanted to see if we can actually use those methods and see if we can actually generate our own method that would be ideal for our particular data. And Ancestry has lots of data, especially lots of name data, lots of geographical location data. So our goals were threefold. First, we wanted to produce a data-driven method that would improve our recall and also be precise enough for our purposes. We also wanted to generate a training data set that we could want to share with the wider community, so anybody could actually use our training set and generate their own models. And the third goal was to compare our method using, kind of rigorously compare it with the existing methods out there. So we were motivated by collaborative filtering, something similar to what Amazon or Netflix does when they recommend you movies or books. Our actions of our users actually suggested us labels. So our users, when they interact with our website, they search for relevant documents for a particular person on their family tree. Then they attach those documents to the actual relevant node. So they kind of become like they actually bring us the information and bring us the linkages between the data. Also, users use search and they reformulate their searches. We can capture all this information in our logs. Then the idea is when we actually collect the data, how we can use this data. We can try to divide the data into negative and positive classes. And positive classes may be relatively simple to identify, but negative class is more difficult in this case. How do you know for sure that two names may not necessarily be spellings of one another? Maybe the user knows better. So at the end, we decided to use the parallel corpora method, where we basically use all the data, and we're not going to divide it into classes. So the two processes that we early identified as the sources of our data sets were what we call the records data set and search data set. So records, like a data set, is basically like I already mentioned. It's this linkage between the tree node of some person and a related document connected to that node. So you can find the name information in a tree node. That's how users specify the name. And in the record, that's the official record. You can also find the same information as well. And very often, this information is going to be identical. But often enough, it's not identical. Often enough, it's actually, there are significant differences. And that will give us training data. Search data set is basically reformulation data. Again, we basically captured user searches. We captured it in time. We basically looked at particular user at certain time, found what he was searching for, and then looked at the next searches of the same user in a certain period of time. Then we captured this information and created the pairs from this as well. So now we had two independent data sources, and we wanted to build models using this data. Here on the right side, you see the image of basically some example of different distributions on the left side of our pairs and the right side of our pairs. While you would think that in the search reformulation, distribution may be similar, in our records data set, distribution is significantly different. Because in the tree nodes, it's typically the last name spellings by modern users, how they actually think the modern spelling is. While in the records, the distribution is different. It's skewed to historical spellings of last names. Because our data contained errors, it was really critical for us to set up a pipeline shown here for cleaning the data set. The two important steps in this pipeline are co-occurrence filter and Jacquard coefficient. In the co-occurrence filter, we basically selected top co-occurring pairs to be left for training sets. And Jacquard coefficient, we wanted to discriminate against high-frequency individual names. For instance, if there will be a pair of Johnson-Smith, we wanted to kind of remove those pairs as well. Even so individual Johnson and Smith would be very high-frequent names, we wanted to discriminate against those pairs. So now that we have a kind of clean enough training set, we decided on the method we're going to use to train the model. We looked at machine translation, and we've looked at our problem as a kind of a translation problem, where on the left side you'll have one language, which consists of names only. On the other side, you'll have another language, which is basically different distribution of names only. And the idea was to basically use machine translation method and calculate kind of alignment rules that would show us the basic rules that would be needed to apply to certain names to translate them into other certain names. In our case, we treated machine translation problem a little differently. So we had a certain caveat that the individual words would be actually characters, and the sentences would be just the complete names. Here on the top of the slide, you see the basic formula from machine translation community, but again, slightly modified for our purposes. What we wanted to find is the k maximum probabilities of target name given source name. And what it equals to is again, k maximum products of the name model and alignment model. So I'll go in a few more details what they are. Our name model is just basically a statistics describing a target language. And the way we actually implemented name model using n-gram, where n-gram is just the probability of the certain letter coming after n other letters. There are multiple actually open source solutions to actually calculate the name models. Alignment rules are actually what was the point of actually training the model. So alignment rules were well computed using expectation maximization method. And here I can give you like a brief, simple example at the bottom where you see typical alignment rules. Like you see those arrows from one spelling of a last name, Thorogood, to another spelling of the same last name. And you see that OU results in one letter O, while the other alignment rule is 2G and H disappears and 2G's become single G. That's another alignment rule that was produced by our model. But there are produced tons of other alignment rules. Now, the idea was to actually, when we actually got the model and we actually experimented with it, we wanted to compare it with other methods using the same common framework. The methods that we selected were commonly used in our search engine and commonly used in other databases as well. Those are phonetic methods, including soundex, dimetaphone, NYCs, and a couple of other methods. And the string similarity measure, so that's another class of methods we wanted to compare against. We identified Levenstein, Jarrow-Winkler, and Winkler method. And our method was machine translation, which was implemented using Moses library. So what are just a few words about other methods? So phonetic methods are basically kind of rule-based methods for computing a certain code. So all similar sounding names would actually map into a certain code. And the way this code is computed, actually, that's how each phonetic method is different from one another. For instance, the most popular and very efficient method soundex, which is also not precise, their code looks the following. And basically, they take the first letter from the name and also compute 3-digit code from the rest of characters, and they remove all vowels. NYC is a different method, and it actually has all character code. They don't have digits. This is just a basic example of codes produced by different phonetic methods. Another class of method we compared against was similarity methods. And similarity methods can be shown here using example of edit distance, also called Levenstein method. It's basically, it comes from the edit distance, and the idea is it's a number that represents a number of simple operations that you need in order to convert one string into another string. And simple operations are basically deletion, insertion, or substitution. This matrix just shows how the actual edit distance is implemented. The actual similarity is being computed from the actual edit distance by this formula. So you actually divide the edit distance by the length of the maximum string, and then you subtract this value, which is the value between 0 and 1, from 1. Then you get actual similarity value. So now to our standard kind of evaluation framework that we used. We used the standard evaluation framework in the sense that we wanted to actually help some of those methods to compete with data-driven method. For instance, phonetic methods, they could only return a binary result. It's either the last name is, 2 last names are in the same, considered to be the same because they have the same code. Or they're not considered to be similar, then they don't have the same code. So it's basically 1 or 0 answer. So we wanted to actually, our common framework looks like this. We had alignment scores produced by basically our methods. It's either machine translation method, similarity measure, or phonetic method. And then we multiplied by the language model score. And language model score we compute for machine translation. We also computed it for similarity and for phonetic methods, just to be fair to those methods. Here are our results. This result shown using records data. We basically show a precision recall graph where you have curves for each individual method that we looked at. We use the 10-fold cross-validation here, so we train on kind of 1/10 of data that we had, and we train on the rest. And we tested on the rest. And we didn't, so basically for every method, we generated 10 curves. So here you see those 10 curves shown as kind of a confidence regions around the centroid curve. So in order for the method to be the best method, it has to be closer, its curve needs to be closer to the right top corner. So on the right top corner here, you see actually Moses 5-gram method. That's the basic machine translation data-driven method. It's 5 gram because that's what we chose from other possibilities for our language model. We tried experimenting with 2 gram up to 6 gram, and 5 gram apparently was the best in our precision recall. The worst performing methods were phonetic methods. And out of phonetic methods, what we found curious that NYC's method was performed better than all other phonetic methods. This was also an important finding of this work on our data, of course. The next best methods were similarity measures, but it's kind of difficult to say from our results which of the similarity measures were the best because their confidence regions were overlapping. But what's one thing is for clear that our method was better than other methods we looked at. So we got very similar conclusions from our second data set from search reformulation. And that gave us more confidence because those 2 methods were produced by completely different processes. So we used primarily Moses kind of open source library for our machine translation needs. We use IRS-TLM package to generate a language model. And we use Giza++ package for statistical character alignment. We also used the Federal Library with Peter Christensen from University of South Australia for implementations of similarity measures and phonetic algorithms. We also implemented some of them ourselves, and we also used other libraries just to compare. So in the conclusion, our finding basically showed that on our data, our machine translation data-driven method significantly outperformed other methods and became deemed to be useful for our query expansion in our search engine. So now it's actually being incorporated into Ancestry search engine, and it will improve precision and recall. NYC's phonetic method showed up to be significantly better than other phonetic methods. And that's another thing we're also trying now, because we use soundex in other cases. In other kind of services with the company. And we also share our data set with the community, so you can find it on this URL. It's also in the paper. We published a paper on this in ICDM in 2014. That's it, if you have questions. That's right, yes. This actually more applies to also geographical locations. With first names, there are problems, let's say with cases like Richard Dick, which it basically, you can't come up with the rule here because it's really exception. So we're actually thinking about this right now, because we also experiment with this for first names, and it's not that great because of that, because we really want to capture those things. So we want to kind of change our whole idea, but I think we still can use, can use our pairs. But for instance, one solution would be to just pre-compute statistically, kind of using collaborative filtering, and say for common first names, just go to that table. But then the whole benefit of this is that you don't have to have all the names in your training set. Here you can find some kind of new name completely, but still use the same rules to come up with alternative spelling set. If you would just use a table, that would not be the case. So that's still kind of ongoing effort. On what? Unfortunately, our whole data set is coming, I forgot to mention that most of our users actually are Western Europe, US, Canada, Australia, New Zealand. So we have some data from China, and but not enough for us to try it. But that's definitely a goal. If we find the data, we would love to try it, but we don't have it yet. We tried on Eastern European languages, and that works fine. Any other questions? All right, thank you.